Hi there, guys. Well, welcome back. We're motoring through this. We've just done 4i. We're about to do 4j. They don't give a title for it, but it's essentially the product rule. So we're going to prove the product rule. We're going to talk about it a little bit as well, and we're going to apply it. Perhaps we're going to apply it first. Maybe that would be a quick way to see why this is useful. Okay, so what they're talking about essentially is two functions. So let's just click on that. So we're saying that, I don't know, y is equal to two functions. We can call them g and f if you like, but they're not functions of functions in this case. They're just, it's y of x is equal to u of x times by v of x. Okay, so we're talking about y being a product of two functions. I don't know, like for example, let's have 3x cubed and x squared minus 1 to the power of 6. Well, here we have a product of two functions. This isn't the chain rule because we can't say that this is just a function substituted into a function because, well, what's the function inside the function? This is in fact a product of two functions. Okay, so we need a new rule for this one. Okay, so this is how we're setting it up. Sometimes you see this written as y equals uv instead. And we're just saying, well, sure, all of these things are in terms of x. We're always differentiating in terms of x. Now, if we look at how they write this one down, they say, well, check it out. We're saying differentiate one of the functions, differentiate the other function, and then times by the opposite function and then add them together. So they're saying u times by the derivative of the other function, v dash if you like, plus v times by the derivative of the other function, vu dash. That's often how people write it down in shorthand. Okay, so if you want to work out what y dash is, or dy dx, we're going to use the product rule, we're going to use this. Okay, well, we're obviously not proving it there, but I will come up with proving it at the end of this exercise. I know that there's an investigation on the front which leads you to that, but I'm not going to do that at the moment. I'll do that at the end. So there's actually only two questions here. So again, let's do those two questions. The rule is pretty easy to remember, but it's also given in the formula booklet. This one says, use the product rule to find f dash of x when here are your two functions. So always set this one up in terms of the two functions to start off with. So that's our u, this is our v, so we've got 3x minus 1. U dash, or du dx, is equal to minus 2. V dash is equal to 3. So when we stitch these things together, we'll get f dash of x is u minus 2x times by 3 plus v times by u dash, which is minus 2. Okay, and now we need to just multiply those out. So we've got 9 minus 6x and minus 6x plus 2 there. And, no, they're not. I thought they were cancelling. No, they're not. We've got 11 minus 12x there. Okay, so that's our answer in this case. You can see this is a really quick way of doing finding the derivative of this function here without actually multiplying out your two functions or multiplying across your two functions. Happens to be a polynomial in this case, but later on we'll deal with other types of functions like log and sine and e to the power of something. But at the moment we're just dealing with polynomials. Okay, now obviously in this function, if you want now the gradient when x is equal to 1, you just substitute 1 in here and you'll get your gradient. This is the gradient function. We know that already. Okay, so 11 minus 12x, let's just check I've got that right. Yep, got that one right. And example 22. Okay, find the equation of the normal to the curve. We've got here, we've got 3x squared minus 1 divided by x plus 2. Now, normally I would treat this as quotient rule. Now, there's a different rule for the quotient rule, and that's what we'll do next time. But I know why they're doing this is they're building you up to the quotient rule. by saying, well, we can deal with this as the product rule. So we can say that this is really 3x squared minus 1 times by x plus 2 to the minus 1. Okay, so we can now write down that u is 3x squared minus 1. V is x plus 2 to the power of minus 1. So we can actually see that we've got a function of a function there as well. So we're going to have to use the chain rule with this. Now we got u dash is equal to 6x, and we've got v dash is equal to, now hopefully you've had enough practice with the chain rule now to realize that you can do this quite quickly. We're going to say let's times by the minus 1, let's reduce power by 1, and let's times by the derivative of what's inside, which is 1. So now this is equal to minus 1 over x plus 2 squared. Okay, so there we go. This can go on the bottom with the power of 2 and minus in front times by 1 at the end. Okay, so good. So now we've got, so essentially that used the chain rule. So now we're going to write down our y dash, if you like. So y dx. To be honest, I haven't really read the question well. It says find the equation of the normal. I need a bit more space after this. Okay, so dy dx is equal to u x squared minus 1 times by v. V is x plus 2 to the minus 1. And then that's going to give us, the next one is going to give us plus v. So that's, sorry, I've made a mistake, but that's u and I've just times by v. I need to times by v dash. There's a minus on the front here as well. And then we've also got plus u dash, which is 6, and times by v, which is x plus to the power of minus 1. Now, what do we need to answer? So that's our long derivative dy dx. And now they say that we want the normal to the curve at this particular point here. So we're going to need to substitute in 0 in order to get out the derivative at 0. And they've actually given us the point itself. So they don't just say when x is equal to 0, otherwise we need to find y to find our coordinate point in order to come up with the equation of our normal. But we do need to find the gradient when x is equal to 0 as well. So our gradient here, I'm just going to write m actually, is going to be when we substitute in x is equal to 0. So let's write that down. So when x is equal to 0, now this is the gradient of the tangent, not the normal. So we'll need to do the little trick to get the gradient of the normal as well by doing the negative reciprocal. Anyway, when we substitute 0 in, we can see we're getting minus 1 and 2 to the power of minus 2 there. And this whole thing is just going to be times by 0, so it's going to disappear. Now, by the way, we could obviously write this in a different way. And we could put, for example, x plus 2 on the denominator of this fraction here, and then get x plus 2 squared rather than x plus 2 to the power of minus 2. And you'll see when we go into creating the formula for the quotient rule, okay, so when we come up with the quotient rule and consider this as a quotient of two functions, in other words, a division of two functions, you will see that you actually get v squared on the bottom of the entire thing. But we'll deal with that in the next exercise, of course. So when we times this across, when we times this one out, we get 1/4. So this is giving us a quarter here, so squaring and taking the reciprocal, which means that m of our normal, like we can say, it implies that the normal gradient is going to be minus 4. And now we can set up y equals minus 4x plus c using this coordinate point here. In fact, we don't even need to solve an equation here because we can see that the y-axis intercept is 1. That's what it's telling us. When x is 0, y is 1. So we've got y is equal to minus 4x there plus 1. There is our final answer for this question. let's just check that one across. There we go, yeah, minus 4x and then plus 1. Okay, so now obviously a lot of people will just want to plow on with some practice here, but you could be asked to do proofs in an exam situation, especially in some of the extended questions. And I think we should try and prove this as well, because it's not particularly difficult, apart from there's one little trick in the middle. And it's kind of an interesting little trick, to be honest. So in terms of setting up our derivative, so dy dx, then we'll say we're looking for the limit as, let's go back to using h, as h tends to 0, of, again, of course, we're doing f of x plus h minus f of x divided by h. So that's just our formula, or our definition of differentiation from first principles, which is given to us already. So it's given in the formula booklet. Now we should say that y is a product of two functions here. So let's call that function u and v. And if you want, you can call those u of x and v of x. In fact, that might be quite useful here because we're substituting things in. So what we're going to write here is say that this thing is in fact us saying u of x plus h, and because this is a product of two functions, then the function itself, which I'm flicking to the notation of y for, so this is really f dash of x, but same equivalent to dy dx. Now that's equal to u times by v with the x substituted in as well. So there's our product of the two functions, giving us our original function, which I'm calling y rather than f of x. Take away, right, take away u, x, v, x, and all divided by h, and this is the limit as h tends to 0. Now, it's difficult to see how this is going to be taken further, because what we're working towards, of course, is u v dash plus v u dash. So somehow I want to engineer some factorizing out of u, and then I want to be left inside with v of x plus h minus v of h once I've factorized out my u. And you can see, look, I can factorize out my u here, but I'm missing that here. Okay, so I need to create that. I need to create another term. I need to create another term which has got v of x times by u of h plus x plus h, or vice versa. In fact, in this case, it's the other way around. I need to create the extra v of x plus h in order to take out u. Okay, so this is kind of a bit tricky here. So let's just leave that one open on this side, and let's just go to the next line and say, well, okay, let's then add in here, well, we need another v of x related to u of x plus h. So what I'm going to do is add v of x and then times by u of x plus h. So now when I factorize out v of x from these two terms, I'm going to get this take away this, and that's going to give me my derivative of u. Sorry, I'm doing it the opposite way around. I'm aware I said u v dash. I was talking about that term, but now I've gone into talking about u dash and by v. It's okay. It doesn't matter. It doesn't matter which way you do this. Okay, so we've got that. So we're factorizing out v, and we're going to be left with our derivative of u. Okay, now if we add this thing, well, we need to subtract this thing as well. So we're adding and subtracting the same thing here. So minus v of x u of x plus h, and that thing is all just divided by h. Now I can do some nice factorization. I can say, okay, well, let's take out that v, Okay, so if we take out the v of x from, you can see we can combine these two fractions because we have the same denominator. Now if we take out that v, then that's the v from here and the v from here. And sorry, it's the v from here and the v from here, because we want plus this and minus this. So we're getting u x plus h minus u of x. Okay, now that's all over h, and I'll just incorporate the h there. You can see that that's the definition now of your u dash. When we bring the limit inside, which we can do through the properties of our limits. And what are we getting on the other side now? So we want to factorize out u. So what have we got? We've got these two terms here. We've got this term and this term here. Now, we can see that we can factorize out u of x plus h. Well, we really want to factorize out u of x, in fact. But it turns out we've just got u of x plus h here, u of x plus h. Now, we're left with vx plus h take away vx. And again, that's in some brackets, just like this was in some brackets as well. Got to put those brackets there. But I did a divide by h, so that sort of sorted that one out. Okay, and likewise, I'm going to do the divide by h here to keep that as a single fraction. So we're sort of doing that and that. We've factorized out these things here. And we've got a plus in the middle. Okay, now you can see quite easily that if I bring my limit inside, I can do my limit on this and on this and on this and on this. Okay, so I can do that using the properties of limits. Now, the limit as h tends to 0 for this turns out to be u of x, pretty nice. And the limit as h tends to 0 for this is v dash of x. And then we've got the limit of this, well, that's dependent on h at all, so it's just v of x. And then the limit as h tends to 0 for this final part is going to be u dash of x. There we go, we're done. There's our final formula. Okay, so there's the proof that a product of functions, if we differentiate it, we end up getting the original function, or one of the first function, times by the derivative of the second, and vice versa, added on to the end. Okay, well, thanks for listening to that. I think I'm missing a bracket on the end there. There you go. And you can see that that's done in an investigation there. And I think they've done it the same way as me. They've got u, they're adding on u x plus h. Did we do that? Yeah, we added on u h plus x plus h there as well. So we did it in the same way. But of course, you can do this in a different way. You can add on u of x and v of x plus h, and you'll get the same answer there. You'll just get v of x plus h in this case, but which will tend to be v of x anyway. Okay, so there you go, that's done. And you're going to have a go at the questions from 4J now. 10 questions there. And next time round, it is no doubt talking about the quotient rule. Okay, so quotient rule is going to be a division of two functions instead. But okay, that's for next time. Thanks for listening in, and good luck with the exercise, and hope to see you next time.